Hello, everyone. Welcome to the Room of Lives, where we sit with humans and get a taste of their life through their stories, thoughts, and ideas. I'm your host, Neil, and today I'm sitting down to talk to my really good friend, Stefan Eccles. Stefan is a fellow physics PhD student at the University of Texas at Austin. He researches theoretical cosmology and will tell us about his job of probing the universe at both the largest and smallest scales you can or cannot imagine. We'll also talk about the very active outdoor life of this scientist. Stefan has been called Mountain Man by friends. He's a champ at climbing and camping and starting a fire and hiking for miles while carrying other people's heavy stuff. More recently, he has gotten really into jiu-jitsu, and not simply for the pure strength aspect of the sport, as we will discuss. Okay, so if all these aren't enough for a lifetime of hobbies, Stefan's also had a bit of a career in music. He played the drums, writes and sings songs, and today he's going to sing us an original composition called Time Machine that I really like. At the very end, Stefan will share with us his experience of growing up deeply Christian in Mormon, Utah. In that context, we'll talk about ethics, free will, and spirituality, and he'll share with us how his personal evolution in the academic world has gradually made him distant from his more religious community back home. We'll finally end with what Stefan thinks the future holds for a scientist like him. So, in this first part, we'll talk about how the trajectory of his life brought him into physics, and about the fascinating questions in cosmology that he and his colleagues are trying to answer. So please join me in welcoming Stefan Eccles to the Room of Lives. Welcome to my podcast, Stefan, and thanks a lot for doing this. So, if you could tell us a little bit first about who you are.
Sure. Well, first, thanks for inviting me. I mean, you basically asked if I'd come and talk about myself, and I'm like, oh, that's my favorite subject, so yes. No. Well, I'm Stefan Eccles. I'm a grad student at UT Austin in the physics department. Known Neil. Neil and I came into the program together, so we've known each other the full time that we've been in Texas. I don't know, any other details that you want there?
Something about where you were born, what kind of physics you're doing.
Okay.
Here.
So I was born in Munich, Germany. I did not grow up there, though. I was only there for about 2 years before my family came to New Hampshire briefly, and then Utah. Utah is really where I was raised. I spent the rest of my life until leaving for college there. The field I'm in is high energy physics. I do a lot of relativity calculations these days. I've bounced around between several topics, so if we get into those things, I'll explain them one by one. But overall, it's just it's fundamental physics, very mathematical, very theoretical physics that's aimed at understanding the very basic forces of nature. A little bit of quantum gravity recently. Yeah. You want me to describe more of how I got into physics?
I would first like to know a little bit more about the exact kind of physics you do. Would you say that it has more to do with gravity and space-time on a large scale, or it has to do with the dynamics of fundamental forces at a small scale?
Okay, well, the group I joined actually does both those things. It's a unique group in that it's got less than 10, but some number of professors like that. They each have some specialty, either in particle physics or in cosmology or in holography or any of these topics. And the students kind of bounce around between the professors and collaborate amongst them. So I came in interested in cosmology, which is the first thing you said, the really large-scale structure of space-time. I have told people that, and they've confused it with cosmetology before, so I always feel like I have to explain a little bit more. So my first project was definitely a cosmology project. That one was related to using quantum field theory to predict signatures left from the early stages after the Big Bang that we can still detect in the cosmic microwave background radiation. That's been a pretty big subject in recent years. And in fact, around the time that I came into school, there was kind of a claimed detection of this special type of signal that could only be created by gravity waves in the early universe. So it was a big deal experimentally, made big waves. I guess it's a bit of a pun.
Yeah.
And my group kind of set out, or at least a couple of us, set out to try and come up with a model that could explain that. Unfortunately, that experimental data was later retracted, and they basically said that they hadn't properly accounted for some contamination from our own galaxy.
Who was it that got this data? When was this?
The group was called BICEP2. It's a group. It's a people all over the place. I think mostly at Stanford, but the experiment was based at the South Pole. So it was a big project. A lot of people, and they're well-respected people. So I think people were a little bit too quick to jump on board with it, but for the most part, they were careful, and it was an embarrassment, kind of. It could have been avoided, but oh well, what can you do? It happens.
What is the form of this data that they collected? Was it microwave radiation? Was it some interferometry or?
Yeah, so they were collecting actually polarization data, and so the cosmic microwave background signal is just this relic signal from back when the universe was in this very hot, dense state. Every time I say that phrase, I think of that little song. But
what song?
I think the Big Bang Theory TV show.
Oh,
they open with a theme shock where they say that exact phrase.
Yeah, and
then it starts going through my head.
Yeah,
but it's true. That's back when things were much hotter. This ordinary matter was not around the way it is now. It was just a big soup of particles, and then there was this critical moment when electrons were able, the universe cooled by expansion to the extent that electrons were able to attach and remain attached to protons effectively. And when that happens, suddenly photons are allowed to stream through that much more freely. So suddenly the light signal, rather than looking like a crazy plasma, it would just look more like just a transparent space, the way we think of it. And photons have actually been free streaming ever since then, and from all directions. That's one of the predictions of the Big Bang model, actually. There should be a signal like this. It was detected a very long time ago. I shouldn't say too much about the history. I'll probably get the dates wrong, but it was first detected just in the form of, a very basic signal, and then it's been mapped out as far as the intensities of this radiation at various frequencies, and it matches the prediction of a blackbody spectrum, which is getting a little technical, but it matched the expectation. The shape of that curve was mapped out exquisitely, and then people started to look beyond that for polarization data, which is kind of roughly, it's the orientation of the photons as they come in. And that is what they were hoping to use to detect this specific signal, which is tensor modes, they call it. But it was the type of thing that was supposedly going to be sourced by gravity waves during the very early Big Bang era. They call it inflation. Gravity waves during inflation would generate this specific signal. And that's what everyone was looking for, because it would kind of be the first indirect detection of gravity waves. More recently, that's actually been done by the LIGO experiment in a much more direct way. It's a different type of gravity wave, but it's they accomplished what BICEP would have maybe made a claim at.
So wait, did you say it is some sort of interferometry, or is it looking at radiation of a certain wavelength?
To detect, to measure to get the polarization data, I think they are doing a type of interferometry. But it's at various wavelengths in this critical blackbody spectrum. So it's corresponding to really low, something like 2.7 degrees or 2.7 Kelvin. But it's so both. I don't know exactly, or I don't know a lot about the experimental signature, to be honest, or how they set it up. So I was taking their data and running with it, kind of.
Can you tell me a little bit about how was it that you got into physics? That's a more general question. And then in particular, how you got into this particular field of physics that you're working on.
Sure. Yeah, I knew that you were going to ask me that, so I was thinking about it. And I had all these factors kind of pointing me in that direction, but I didn't recognize it until really late in the game. I didn't actually become a physicist until halfway through my undergrad days, but, going way before that, you could have maybe predicted it. The first relevant fact, I think, would be my father's a physicist. Other than whatever genetic disposition he gave me, I don't think he really pushed me in that direction at all.
Yeah. Do you think there is any actual genetics involved?
I think there is. It's uncanny how similar I've turned out in ways that I, wasn't aiming for.
Yeah.
So I think there is similarity in thinking, I guess.
This is a bit of an digression, but I would still think that although you're not consciously aware of making deliberate choices in the direction that your father did, there could always be subliminal conditioning from growing up in a certain kind of household, as opposed to an actual physiological inheritance from the genotype. And the reason I say that is, I think it's kind of funny that I'm actually deconstructing this, but my understanding is that the genes, they shape, to some extent, they shape the construction of the nervous system and the brain. So what could be inherited, I guess, is the propensity for certain kinds of certain kinds of mental aptitudes like curiosity or intelligence. But to inherit curiosity for a particular field of human knowledge, I guess, might possibly be a social or cultural conditioning that rides on top of the physiological inheritance. I've thought about this for the last 5 minutes, so I know it must be true, but yeah, I just happened to think of that.
Well, no, I think it must be true because, it has to be a combination of the two, and I wouldn't know which one to give more credit to. Although, just based on how I wasn't expecting to turn out so similar to him, I don't know. It still could be both, I guess.
Yeah.
And as one friend of mine pointed out recently, it at least put physics on my radar of like things that people do, even though I didn't understand it at the time. In fact, I would say I really had no clue what a physicist did, despite the fact that he was one. He would describe his job to us as space weather, which is a pretty accurate description. He models really high upper atmosphere physics. But beyond that brief description as a kid, I had no idea what he was doing at his computer. And I didn't care that much. Like, it sounded kind of interesting, but it wasn't enthralling to me, the idea. So I never paid much attention to it. And going up into high school, I still could have seen myself becoming anything. I was interested in history and philosophy, and actually that also is kind of like my dad. But I could have seen myself going any number of directions until, I guess, calculus class and physics class. I at least started to learn that maybe I was a little better than average, or I started to gain a reputation in those classes that made me think, okay, at least maybe it'll be easier for me if I go in this direction. And I guess I started to notice that I thought about those subjects differently or appreciated them more than most students. Like, when most people are groaning and complaining about how they're never going to have to calculate the area of some curved shape or the volume of some curved shape. Me, when that subject is brought up and I realize I don't know how to do that, and I think, you've given me the equation for the surface. I know the information is there and contained, but I'm like helpless to extract it, and the only thing between me and getting that information is just my lack of ingenuity or whatever. Not that I care about the volume of things particularly, but just the fact that it's a puzzle and I know that I should be able to do it and I couldn't. And then I realized all that I do know how to do is like squares and triangles on that same topic. I felt, that's so limited. And then once it's explained to you and you go through a little bit of struggle to understand it, I found that process very rewarding. Whereas everyone else, I think, still is just moaning and complaining. It doesn't, and it's not that I wanted to then immediately set out and go compute a bunch of volumes of things. Once I have the understanding of how it works, I don't care about it anymore. It's like, so that I think maybe differentiated me from the engineers, but I also wouldn't realize that until later. I also had a really good physics teacher, but intro physics classes, I always feel, are touching on a bunch of individual topics that don't seem that connected at first, and neither are they that interesting, individually at least. Part of the fun in physics comes with kind of drawing deep connections much later, but you can't really do that for a while, so I don't know how to solve it, but I've always kind of had a complaint about intro physics classes. But that teacher was at least helpful and encouraging and challenging at the same time. So anyway, I think my mom's advice was, oh, why don't you just go do engineering? That's kind of math, science-y, and it's a good career route. Very
By
practical.
the way, quick interjection. You said that your father was a physicist. What did your mom used to do?
She had a degree in wildlife biology, and then she was a stay-at-home mom for a good number of years, this whole time period. And then afterwards, she actually went and got some medical training and has been working at a doctor's office ever since as a, I always forget whether it's a medical assistant or a physician's assistant. I know there's a big difference between the two, but I forget which title she has. But yeah, so she had an interest in nature, which I would also share. But it was, I mean, to her chagrin that I would follow my father's footsteps towards physics, because she hates it when we get together over the dinner table and start talking physics. She's very vocal about hating it too. It's funny, but oh well. So yeah, then I went on to college heading towards an engineering degree, and of course the curriculum starts out pretty similar to physics, but as I got maybe 2 years in, and I had a good friend who's a physicist, or a physics major, and I looked at his prospective course list versus mine, and I realized that all the things on his list I thought were just fascinating, relativity, quantum mechanics. I wanted to learn that stuff, versus mine was like CAD software training and things I didn't particularly care about. Only then did it really dawn on me, like, yeah, I don't have the mindset of an engineer. I really want to be a physicist.
Had you declared a major for a kind of engineering at that time?
I was in mechanical engineering.
I see. That's not too far from...
Yeah,
at least in the introductory stages, it's not too far from physics.
Yeah, exactly. Which is why 2 years in, I was able to switch, and I did have some gaps, which I think even still I find it a little annoying that I never got that training early on, but it was pretty easy to make the switch. So just in the nick of time, I got to take, the relativity instead of the CAD software, things like that. And relativity is actually one of the subjects I fell in love with pretty much immediately, because it introduces all these concepts that seem nonsensical.
Yeah, it's crazy.
Yeah,
it's crazy. It's pretty crazy.
Yeah, every particle, every object has its own time, and somehow everything remains consistent. That just, it seems like nonsense to me. But with pretty simple math, like really you can get by without even calculus to understand most of the concepts of special relativity, at least. Not to say it's going to be easy. I mean, I recommend that people do that if they're even remotely interested in the topic. Pick up an introductory book on special relativity. I think mine was called A Traveler's Guide to Space-Time or something like that. But it was actually
A Traveler's Guide to the Galaxy.
Yeah, pretty similar. I wonder if he was playing on that. But I had so much fun just thinking about those concepts, probably when I shouldn't have been even, and trying to figure out how it still all made sense and didn't just result in a bunch of contradictions. And then I think a lot of students fall in love with quantum mechanics first. Yeah, what did you fall in love with first?
Well, before I talk about that, you just reminded me of this little episode that happened in a relativity course during my undergrad. There was this professor who, by the way, I did not like so much because I thought I didn't understand a lot of the things that he was teaching. So he was teaching us special relativity at the time, and it was, I guess, day one of the course. And so he drew this diagram on the board of circular wavefronts of light emanating from a source, and then they are being received somewhere else, and some geometry of the time difference or something. And in these calculations, he already involved relativistic arguments or understandings without introducing them first. So he just said, well, it's going to be this way, So he was already using this relativistic metric that he hadn't bothered to introduce or talk about at all. So I was tangibly bothered by this, sitting towards the back. So I raised my hand and said, I don't really understand. How is this? Something about simultaneity or something like that. I said, it doesn't make any intuitive sense. What is going on here? And he was pretty perturbed by this question. He got a little annoyed, and he said, I don't really have time for all these philosophical problems that you have. A lot of people have been having philosophical problems with relativity down the decades, and it has never gone anywhere. So I think if you are interested in these kinds of things, you should do something other than physics. But if you want to do physics, you should just go with the math. And the math is a simple rotation in hyperbolic space. I don't understand what all of this trouble with relativity is about. I see it simply, it's just a simple rotation in hyperbolic space. And so those words ring in my ears still. Like, if anyone ever has any trouble with relativity, I'll just tell them, it's just a simple rotation in hyperbolic space.
That's funny. Yeah, I always wonder if someone is tasked with explaining it and at an introductory level. Often they're not people who really do relativity, so they don't even understand it. I mean, that definitely happens.
Yeah.
I've seen, to be fair, not many people need relativity for their daily work, so there are plenty of people who do really good physics and don't understand relativity.
But coming back to your question, I think the first time I started going down a trajectory of interest within physics that was going to last was when I started getting into computational physics, because I really discovered that I liked programming. I liked solving problems by writing programs. And so one good thing that happened during my undergrad education was the very first semester of the first year, we were taught Python and ways to use Python to solve dynamical physics problems. And so I started getting into computational physics, and eventually that led to an interest in nonlinear dynamics, and that eventually led to a wider interest in complex systems, and that eventually led to a migration into computational neuroscience, and now I'm doing research in vision. So it's been that's been the trajectory for me. Yeah, so coming back to what you were talking about, could you give me sort of general layman's introduction to the research that you have done in graduate school so far?
Yeah, sure. So I sort of already talked about the Cosmology project, which was me learning about basic cosmology and learning about quantum field theory and how you do basic quantum field theory calculations in curved space-time. And if you basically if you say, such and such quantum fields are the basic ingredients at this time, or really early on in the universe, what does that result in the CMB today, the cosmic microwave background radiation? What signal does that leave behind? So that was a pretty popular subject at the time. Still a lot of people do it because you can play with various combinations of fields, really simple models, complicated models, whatever. So the second, that project did not end well, partly because the experimental motivation for it faded, and plus there were some errors in our understanding of it, really, which by the time we realized it, myself and the other grad students we were working on, it took us too long to convince to convince our major advisor that we were doing it wrong. It's a small grudge. I really like my major advisor, but it took us.
How are you just afraid that this is going to go on the air and going to jeopardize your relationship with your advisor?
Who knows? No. Anyway, we did end up wasting time near the end of it, in my mind, pursuing it past when it should have been pursued. But, and that left a bit of a bad taste in my mouth. But then I hopped over to another topic that my advisor had been mulling over for a while. It was pretty unrelated, but it's in the field of, general relativity and thermodynamics, which is a field that Hawking and Bekenstein started many years ago when they did some basic research about what happens when you put quantum fields in the vicinity of a black hole. And they discovered that...
So, quick interruption there.
Mm-hmm.
Was the reason that they were interested in this the fact that the effects of curvature by gravitation in the space-time is greatly pronounced or amplified in the vicinity of a black hole, so the effects would be easier or more interesting to calculate?
Definitely more interesting. It's supposed to be a fertile testing ground for any idea that you might have about quantum gravity, because those two theories, quantum mechanics and general relativity, have never played nice together. We still don't know how to put them together in some consistent framework. It was done a little bit, kind of partial. I mean, the intermediate step is called quantum field theory in curved space-time, where you basically leave the background geometry of the space-time is curved, but it's fixed, and you don't. It's not completely. The interaction no longer goes both ways in the fullest extent. You just put quantum fields on top of this fixed background, and that's kind of what Hawking was doing. But in the vicinity of a horizon, suddenly that amplifies all the things that you don't understand, because the horizon of a black hole is a confusing area anyway. Even in classical general relativity, it took people decades of argument to land on an understanding and a solid mathematical understanding of what the horizon is and what happens if you try and go through it and things like that, according to pure general relativity. And then add the quantum mechanics, and there's a whole new layer of confusion. But anyway, Hawking's calculations show that black holes actually radiate. They spit out particles in this another black body spectrum, which is basically the type of radiation you get when any object is just thermally emitting, meaning it just has a temperature and there's an associated emission. So you and I emit a black body spectrum. It's not invisible light. It's, where our temperature is kind of corresponding to infrared wavelength. So if you look at us with infrared goggles, you will see that emission. But any object with a temperature emits. People would have said, excluding black holes.
But did you say we emit a black body spectrum of radiation?
Well, we do more than that. We also are reflecting. That's mostly what you normally see. But there's also just emission corresponding to our thermal emission, which is mostly in infrared for human body temperatures. But people would say any object with a temperature, which is basically any object at all has some thermal energy, is going to emit radiation just more or less through those random thermal processes. And it's always going to be in this black body pattern. It's just the name given to the shape of a certain curve. But people would have excluded black holes originally because they don't count as an object in the normal sense. And the whole point is nothing, not even light, can get back out. So how can it emit photons or any particle at all? And yet Hawking showed that it does. So it does have a corresponding temperature. It's extremely low, but it exists. And, that launched a whole field of interpreting what the temperature of the black hole means, kind of. And then fast forward more than 30 years, and my advisor had this idea about trying to associate a temperature and an entropy with other types of objects or other types of solutions in general relativity. It had already been done with other types of horizons, but he wanted to do it with this particular object called a shockwave in general relativity. It's another solution that it kind of corresponds to a single particulate source, or any source actually traveling at the speed of light. So it would map a photon, for example, or a particle of light travels at the speed of light. If it made a substantial gravitational back reaction, which normally it doesn't, but if you had an extremely energetic photon, it would, then it would create this shock wave.
What do you mean an extremely energetic photon? I thought that they all travel at that same speed.
Oh yeah, it's not the speed decreases, but when a photon, if you're talking about high energy or low energy photon, that in quantum mechanical terms that corresponds to longer wavelength, shorter wavelength. They travel at the speed of light regardless. In general relativity, if you can associate this really high energy with it, suddenly it becomes important even gravitationally, and it is kind of this wall of gravitational effect that travels through the space-time. So it's this exact solution in relativity, which those are surprisingly hard to come by. But anyway, he wanted to do some thermodynamics with this thing, and he had some really good ideas in my mind for how to diagnose it. But he also had some particular theories about how it should work, which were not maybe the mainstream theories. So when we got things that didn't match his expectation, we kind of didn't know what to do with it. We didn't know how to interpret it, so we gave up on the idea eventually. But I spent a lot of time learning how to do that sort of calculation, and it was a fun project for that reason. And then recently, I've switched to a third project. I mean, I've had other small projects in the meantime, just brief calculations on other things with other people, but these are the big things I've really been invested in. Recently, I've started to get into one that falls under the umbrella of ADS-CFT, which is, it stands for the Anti-de Sitter Space Conformal Field Theory Correspondence, which it's a bunch of jargon, but kind of it's about this. So when we use the word correspondence, we're talking about the fact that these two completely different systems, one is a quantum mechanical system and one is a general relativity, gravitational solution, they have a correspondence in the sense that they seem completely unrelated, but there's this mathematical relationship between them such that if you answer a question in one of the systems, there's a corresponding question which you've answered in the other system, and there's this one-to-one relationship. There's a dictionary, they call it. So these systems are related in a way that you would never have expected at first, and because of that, it just so happens that some types of questions are easy to answer in one theory, and if you can translate them to the other theory, they're usually hard to answer questions. And so it's a useful tool, or it's potentially a useful tool. People are really still trying to figure out the dictionary and what sorts of useful things you can do with it. But my current project is doing calculations personally on the general relativity side mostly, and trying to see what it corresponds to on the quantum side in this relationship. We're working with a non-commutative geometry, which is a whole nother topic, but it's just an interesting quantum system, and for that reason we want to see what its general relativity solution does that's unusual and see if there's any interesting correspondences that we can dig up, I guess. But it's all pretty hazy in my mind, to be honest, still at this point, but it's interesting.
When we were discussing this podcast, you said that there are certain plans for the future of your research that you wanted to talk about, the things that you want to do in future. Have you covered those already, or?
So no, not really, and I think I might have even said the wrong thing. But more I was saying I don't know what my plans are, probably. Because I like the research I'm doing now. I enjoy learning it, but I don't consider my track record to be, up to par or where it should be at this point in my, publication career. So I'm not terribly optimistic about the types of academic research jobs I can find after this. I mean, I haven't given up. But originally that is the type of thing I would have said I want to do afterwards, continuing research in one way or another. And if I can keep doing these sorts of subjects, I would love to. But recently I've also played with trying to get into more computational stuff, because I also find that interesting. And it's a skill set that transfers very well to a bunch of different settings. Right now, I just have to hope that whatever mathematical tools I'm gaining an understanding in will prove useful if I end up going to a different market. A lot of people in my group, if they don't do physics, they end up going into finance or something like that, which I think there would be interesting problems in any number of routes. But one of my main priorities is to land up solving interesting problems, whether or not that ends up being still doing physics, academic research, or some other form. I'm not sure.
Would you say that the fact that it has been hard for you to publish, and also the fact that you were a little bit worried about what you would find yourself doing post PhD, is something that is a fairly general concern among people who are researching in relativity?
That's true. That's
if
definitely
you
true.
compare it to other fields of physics or other fields of research in general.
Yeah, relativity is definitely a hard one to find a job in. There's very few people who need to be employed as relativists, strictly speaking. High energy physics is a little bit higher demand, but it's incredibly competitive because it's where all the string theorists and anything from, I mean, there's just a lot of really smart people. I look around at all my coworkers and think, man, how did I get into this group? I also encourage myself thinking at least they can't figure it out either. It's not just me failing on these projects. But it's just highly competitive for, a relatively few number of jobs. That's true. But still, I just count it as a privilege to be able to spend time thinking about it now. At least that's how I'm trying to look at it.
Thank you for joining Stefan and me today in the Room of Lives. If you hang around in the next part, we'll talk about his passion for the great outdoors, about climbing, and about Brazilian Jiu-Jitsu.